grade 10s. Welcome to module number 14. This is our molecular compound naming module. So I'm going to show you how to do the very last rule for naming compounds that we're going to learn in grade 10. We'll build on that in grade 11 chemistry. Okay, so what I want you to remember is you need to be able to identify whether the compound you're trying to name is ionic. Those are the ones we've already done. Does it have a metal and a non-metal atom coming together in a particular ratio? Those are the ionic compounds. And you need to separate those particles from the ones we're going to do today, which are the molecular compounds, okay? And the easiest way to identify which type of compound it is you simply look at the atoms that make it up. If there is a metal and a non-metal coming together, it is always ionic, and then you're going to follow the rules for naming those compounds. They're very different from the rules we're going to use when we name our molecular compounds. So when you're looking at a compound and you have to name it, if it's composed of all the non-metals, well, then you know that it's a molecular compound. It's actually a molecule. And then you're going to use the rules for molecular compounds. So there are two sets of rules, okay? And you need to be able to identify that. So in our next module, where we're going to review everything and do a little practice quiz and lots of naming practices, I'm going to go over again what it looks like, the Lewis dot structure, how those compounds are formed, and how you're showing your work looks very different. Okay, so we, for example, learned the zero-sum rule when we did ionic compounds. And so I've got an ionic particle right here, some salt, sodium chloride, okay? And I'll remind you that in the textbook, this was page section 5.6, and all ionic particles, how they form is very specific. They all create ions, and then those ions come together in a particular ratio. Okay, they have to do that because creating a bond in between the ions is because of the electrostatic attraction that you get between the ions. Okay, so we did all of the work about charges. We did the zero-sum rule to figure it out. We are not going to use the zero-sum rule for our molecules because our molecules don't have ions in them. Okay, so that's the very first thing. You want to be able to clearly identify that this kind of a compound here, like table salt, is made up of metals and nonmetals, and it's the electrostatic attraction of those ions that hold them together. The bonds that they form are called ionic bonds, and these bonds are very strong bonds. They produce really unique physical properties, okay, chemical properties that they have. This diagram will come back to many times in your learning about chemistry because it shows what happens when a molecule like water, that's a molecular compound, comes together to do something like dissolving. And when salt, for example, dissolves in water, you actually get these ions that dissociate, and you get these aqueous ions that are floating around in a solution. And if you were to see what happens at the molecular level, this is what your diagram would look like. Okay? So now we're going to put our ionic compounds completely aside. We're going to remember how to do all of those. But then today we're going to move on to the next big group of compounds. And these are the covalent compounds. Covalent means sharing of the electrons. It's a weaker bond. And these molecules are the ones that are comprised only of the non-metal atoms. So remember when I said in grade 9 it was really important that you remembered which side of the periodic table the atoms were on? You just had to remember that the metals are on the left and the non-metals are on the right. And now we're going to use that. So just look on your periodic table. And if it's a compound that's made up of all non-metals, then it's a molecule. Okay? Maybe it's methane. Maybe it's ethane. Maybe it's water. Maybe it's glucose. Okay, these are molecules, and we're going to use the molecule set. Okay, we didn't use this for ionic particles because there is no such a thing. You have to look at how those ions came together to make different crystal structures. Okay, you learn about the lattice structures and how those particles come together. But today we get to do molecules. So we're going to use our molecule kits. And thank goodness I brought one home. I'm going to show you the fact that these atoms can come together in so many different ratios. Can you see that this one, and this one, all these molecules that I'm holding up in front of the camera right now, they're all made of the same kind of atom, aren't they? The red one is our oxygen, the white one's hydrogen, and the black one is carbon. And they can come together in so many different ways. They don't come together in a particular ratio. And that's why you have to have a different naming rule, because you can't just say something with carbon and hydrogen is going to be carbon hydrogenide. Those are the ionic particle naming. Now you get to count and say, well, look, carbon can come together and bond with the same atom so many different ways. These are the molecules that make up life and living things, okay? So you can have carbon with 4 hydrogens, and you can have 2 carbons with 6 hydrogens. So how are you going to name these compounds? Well, that's the rules we're going to do today, the molecule rules, the naming of our covalent compounds. And the bonds that form between the electrons of these 2 atoms together are actually shared pairs, and this bonding is called covalent. So that word covalent on in section 510, the other word I think of when I hear covalent is sharing. Okay, we are not transferring electrons. There are no ions at all. In fact, these atoms aren't strong enough to pull electrons or to give electrons away. That's what the metals and the nonmetals do, because they're so far apart on the periodic table that they have different pulls for electrons. The nonmetals, they're all on the right-hand side, right? And so they don't have too much difference between the wanting or the pulling. We call that electronegativity for those electrons. So carbon doesn't really want it any much more than hydrogen does. So they're happy and stable by just sharing this little electron. And so we show that shared pair of electrons using these bonds. And that's why all of the molecules that we can build with our molecule set are all covalent bonding, okay? And so that's really important. It's not nearly as strong as the ionic, and so you get things like, the bonds between them are fairly weak, and so water has a very low melting point and boiling point if you consider the difference between this kind of bonding and the bonding that you'd have in salt, right? You'd need like thousands of degrees Celsius to break those bonds because they're very strong, because they're ionic. But when you're looking at water, well, that's a pretty weak bond to be able to boil water and separate those water molecules. It doesn't take too much energy, right? How much energy? 0 degrees to go from a solid to a liquid. 100 degrees Celsius to go from a liquid to a gas, okay? So there's lots of information that you need to know, but we're just going to start with doing our naming, okay? So here's our molecules, and again, they look very different, and I'm going to show you using your Lewis dot structure how you're going to show your valence electrons, because of course they're the ones that are involved in bonding, and then we're going to show how they're shared using a sharing circle, and then we're going to show what a line diagram looks like, okay? So read through this section of the textbook, and please make sure you're spending a good amount of time on all of this work that we need. Okay, so here we go. We've got our covalent molecules, and from the note, you want to make sure that you've written down that covalent means you've got 2 nonmetals together, and of course they are a shared pair. So what do? We draw the Lewis dot structure. So here we go. Here's our water molecule. This is what the actual shape of the water molecule looks like. It's really neat that these kits actually build the right shape for you. So what do? You would show your oxygen, and you would show your oxygen with how many valence electrons? Again, use your periodic table if you need to. It has 6 valence electrons, okay? And you can see that this molecule has 2 hydrogens. There's my hydrogen and there's my hydrogen. So I'm going to just show with a different color here that this pair of electrons is shared. I did not transfer electrons. I didn't show any ions. I'm only showing what it looks like. This is the show your work part for a molecular compound, okay? Once I've done my Lewis structure and I've showed that with my shared pair of electrons, then I can simply draw the actual structure, and that is what a water molecule looks like. Now, How do I know that it's going to be a bent shape like this? Well, you don't really know how to do that yet, but thank goodness that the molecule kits actually are built so they represent the electrons as far apart from each other. Because remember, this would represent a negatively charged region because it's electrons, they have a negative charge, and so do these. So they actually separate and show the distance between those as being equidistant, and that's what makes the molecule stable. Okay, so how do you name these compounds? Again, you'll be given formulas and you have to come up with a name, and you'll be doing the reverse. You'll be given the name and you come up with the formula. Okay, so these are the rules. And again, you keep them very separate. You've learned rules for ionic. Now scratch that. Now we're going to learn rules for covalent, which are the molecules. Okay, so here we go. You clearly identify how many atoms there are in that molecule. Okay, so for this one right here, I did this one already for us. Okay, the chemical name of this compound is carbon dioxide. Reveals some information, 3 pieces of information. It tells me that the atoms that make it up are carbon and oxygen. And it also tells me if I need to look on the periodic table that both of these are made up of they're both non-metal atoms. It also tells me the exact number of atoms that are in the compound. And this is why these rules are actually easier, because you don't have to figure out the ratios and the zero sum. The name actually just tells you how many atoms there are. Carbon, there is only one, okay? You don't need to put a mono, which would refer to one, in the name if it comes first. By just saying carbon, you know that there is one atom of carbon. Okay, so it'd be like one of these little black guys, one carbon atom. Dioxide, okay? Di refers to how many? Do you know that? 2, obviously. So oxygen has 2. Do you see that? And so if you were to write the formula for that, it's so easy. All you do is have a CO2, and that's how you write the formula. See, these are the easiest ones, aren't they? They tell you exactly how many, because remember, these atoms can come together in different ratios. Can you have a molecule called carbon monoxide? Yep, carbon dioxide. So you have to tell in the name how many atoms are in the molecule you're talking about. Okay, now, what are you going to do? You're going to memorize the prefixes. I mean, I think you probably know what these ones are. 1 is mono. 2 things would be di. 3 is tri. 4 is tetra. 5 is penta. Okay, 6 and 7 are the ones that people confuse, so make note of that. Don't make a mistake between 6 and 7. 6 is hexa. 7 is hepta. Okay, people confuse that one. 8, that's easy, octa. Do you know what 9 and 10 are? 9 would be nona, and 10 would be deca. Okay, we'll memorize these in grade 11. We don't have time for too much memorizing here this time because, well, the situation that we're in, but normally we'd get you to memorize those. So write them down and then just be able to refer back to them and use them. Okay, here we go. Let's figure out how to write the name given the formula. Just see how you have to go backwards? Okay, again, it's actually pretty easy. Here's the one we're going to do. N2O3. So place the appropriate prefix before the first nonmetal, unless there is only one, okay? And then you're going to place the appropriate prefix before the second nonmetal. Even if there is only one, we are going to use a mono. At the end, you add an IDE to the second nonmetal. You read it left to right, so nitrogen will come first and then oxygen. Okay, how many nitrogens are there? The little 2 subscript tells you there are 2 atoms of nitrogen, 3 atoms of oxygen, and together there are 5 atoms in that one molecule. Make sure you can do those numbers because that's going to be important for the next set of modules we're going to do. Oh my gosh, my disk space is almost full. Got it. Okay, here we go. So the name for this compound, N2O3, would be dinitrogen trioxide. Do you get it? You need the prefix. That tells you you've got 2 nitrogens. You need the prefix for oxygens, and you change the ending to IDE. Okay, go ahead and do these 6 here or 5 here. Take a break and then do these ones and then check your answers with the solution set. I do want to show you the work that's involved for one of them, and let's do carbon tetrachloride. So take a break, do those ones, and then replay the video. Okay, welcome back. We're going to show you how to do carbon tetrachloride. Carbon would be in group number 4. It has 4 valence electrons. Okay, chlorine is in group number 7. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay, the chlorine in this compound is going to be covalently bonded to the carbon. So I'm not showing any charging. Again, that's for ionic. Okay, the rules for covalent. You show a circle. That's how you show your work. Okay, that shared pair of electrons. The shared pair of electrons, if you only have one shared pair, that is one bond, one covalent bond, a single bond. Can atoms make more than one kind of shared bond? Yes. You could have a double bond, triple bond, and that's what's really unique about our molecules, okay? Then what I do is I show that simply by doing lines, and the shape of that molecule would actually look something like this. If this is carbon and all of these were chlorines, it would be exactly this shape, and that is carbon tetrachloride. Okay, so that's it for naming. There's another one right here. Again, I think this one's fairly easy. Nitrogen trifluoride. Does that make sense? 1 nitrogen, 3 fluorines, and your compound looks like this. Okay, now what I want you to do is do all of that work for the practicing. And then I want to show you on the solution set here a couple things just at the very bottom. I want to show you that there are some molecules that are made up of 2 atoms, and these are the ones that you find as gases. We call these diatomic. Okay? Here's what a molecule of hydrogen looks like. It's never bonded on it. It's never on its own. It's always bonded with another one. There are 7 diatomic molecules. You're going to want to be familiar with them. I'm going to show you a little trick for how to memorize these. Okay? These are the ones, this one right here would be oxygen. This is what oxygen looks like, the one that's in the air right now. Okay? Hydrogen, and you can see the other ones would be just like this. They're always diatomic. So every time you have to write down oxygen, you would never write it as the atom oxygen. You would always show it as O2. These are diatomic, okay? The other thing that's on this sheet here is that there's lots of familiar names, right? Here we go. We don't just call this dihydrogen monoxide. Well, we call it water. So there's lots of common names. This one right here is methane. This is the gas that comes out of the jets in the lab, right? You turn the Bunsen burner on using the methane, and it is carbon with 4 hydrogens, but this is the common name for it. So there's lots of molecules like that. Okay, what's this one? This one's glucose, right? And again, you can see how complex this is, right? This is a molecule, a molecular compound made up of all non-metals. This is what gives you your energy. So this is the molecule that you eat, and anything that's a starch or a cellulose or bigger sugars all get broken down in your digestive system. This is the one that ends up going through your small intestine into your bloodstream, travels to every single cell, gets to the mitochondria. This is the molecule that gives you your energy in the form of ATP. Okay, so it's an important molecule, right? Molecular compound. Now, I want to show you one little trick I want to show you one trick for just getting the, memorizing those diatomics, okay? So I just want to show you what that looks like for 1 second. There are 7 of them, okay? There are 7 of them on the periodic table. And I want to show you how you can memorize them very easily. There's a little acronym for those 7 diatomics, and we say it's Hofbrinkel. I've written that just at the top right here. So add this to your periodic table. Hofbrinkel refers to hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And I want to show you where you can see them on the periodic table. So there are 7 of them, and this is the memory trick for how you memorize which ones they are. They actually form the number 7 on the periodic table if you include hydrogen too. Okay, here we go. 1, 2, 3, 4, 5, 6. And then where's the other one? Hydrogen. Right over here. Those are the 7 atoms that form all diatomic molecules when they're at regular room temperature in our atmosphere. And the acronym again is Hofbrinkel. Okay, so that was a lot of information in one little video, and that's it for today. Our next module will just be all reviewing all of the compounds put together, so our ionic and our molecular, and then that's all the naming that we're going to do for grade 10 science. Okay, good luck with that. Send me an email and let me know how it goes.